In lesson 74, we'll be looking at fluid force, and really the main idea we're going to be looking at is the force on the end of a tank, and that's what most of the questions are going to look like. But this idea is how much force is exerted by a fluid really at a certain depth, and we see that this changes if you ever go swimming and swim pretty deep underwater. Your ears start to get pressure on them, and they start to hurt, and that's because there's more force on them. The deeper you get, you have all the force of the water above you on your ears, and not if you're just a foot deep or a few inches deep, you don't have much force at all. There's this principle, Pascal's principle, that the pressure exerted by a fluid at a depth h, any depth h below the surface of the fluid, is equal in all directions. Also, we see in this little demonstration here, no matter the shape of the container, the force is still the same at that given depth. One important thing to know in these problems, because we'll be dealing with water a lot, that the weight density of water is 9,800 newtons per meter cubed. And we'll be using that when we talk about this fluid force. We oftentimes talk about water. Other times we'll talk about other liquids, and their weight density will be given if necessary. So what we're going to end up doing is looking and realizing each little, let's just take a look at one of these. The force here is going to be a lot more than the force here in this area. So what we're going to end up doing is we're going to find the total exerted on a horizontal area. So one of these, a horizontal area, you're going to find the sum of all the forces on these little rectangular strips. So a lot of force here, less force here, even less force, and barely any force at the top. So the force on one of those rectangular strips is the weight density, because it depends on what type of liquid you're talking about, times the depth, times the area. And what we'll end up doing is we'll use a definite integral to help us sum up all of those rectangular strips. So here's a real simple one that we're going to start with. A rectangular tank, 6 meters deep, is filled with water. So we know we're talking about water here. To a depth of 5 meters, as shown in this cross-sectional view, find the total force exerted by the water on the end of this tank. And so again, realize we're going to have all these different rectangular strips on here. Well, that wasn't a very well drawn one. Really going downhill a bit. But we have these different rectangular strips, and they're going to be different for each one, so we're going to end up finding the force on each strip and then summing them up. What is oftentimes helpful is to put it on a graph, and we can look here. Here's one rectangular strip, much better drawn than my red ones here. We want to find the area of this strip, so it would be the length times the width. See, the width here is dy. Then it depends on how deep, the depth of this, and we use that h for that. So force on a rectangular strip is the weight density times the depth, which is h, times the area, which obviously area of a rectangle is length times width. So we'll take that into account. So let's take a look at this. So what we're going to do is we're going to integrate, and we're in terms of y here, because we're looking at y, so our y values, notice, are from 0 to 5. We don't go as tall as the tank is. We go by how much liquid is in there, or how much fluid is in there. Our weight density, which this was water, so it's 9,800, times the depth. So how deep is this? Well, at its deep, it's going to be 5 meters deep. But how deep is it here? Well, the way that we figured this out, so even just looking at this one, we could think this is at maybe 2.5. Well, it's not 2.5 deep. Well, actually it is, because it's at 5. But what we can do is we can take our height, or our depth is going to be 5 minus the y value. We could see that better if we were looking at a strip down here. How deep is this? Well, this is not 1 meter deep here. We see that this is 4 meters deep from the top. Well, how do we get that 4? We take our 5 minus the y value. So 5 minus the y value. And then we want the area. Well, the area is length times width. Well, this length is constant here. The length is always 8. And the width of our rectangle is change in y or dy. So there's our integral that we want to set up. And now we just have to integrate. Not too hard to figure this out. If we bring out the 9800, we have 9800. We could do a couple different things here, but 0 to 5, distribute this 8 here. So this is 40 minus 8y and dy, and we can integrate this. The 9800 can stay out here. The integral of 40 is 40y. The integral of negative 8y is half of 8, so 4y squared, evaluated from 0 to 5. And I messed up here. Oh no, I have that. So we put in our values, so we have 9800. Put in the 5, we get 200. Put in 5 here, that's 25. Times 4 is 100, so minus 100. We could say subtracting the zeros, put in 0 in there is 0. So we have 9800 times 100 is 98,000. And we're talking about a force here, so we have 98,000 newtons. I'm sorry, not 98,000. This was times 100, not 10, so this is 980,000. And so that is the force on the end of this tank. Notice it doesn't matter how long, it never mentions how long this tank is. Like if we were to put this out here and say, oh, well, this is 5 meters deep or 100 meters. It doesn't matter how long that is. Let's take a look at the next one. It's going to be a little different shaped tank. Here we have our formula again. Make sure you commit that to memory. The figure shows the end of a tank 6 meters deep filled with liquid to a depth of 5 meters. Express the total force on the end of the tank as a definite integral, given that the weight density of the liquid is 4,000 newtons per meter cubed. And so notice it just says a liquid here, it says a liquid here. It's not water, so it's some other liquid that is not quite the same weight density as water. So here's our tank. Again, it helps to put this on a coordinate plane. The last one didn't matter a whole lot, but this one we'll be able to see a couple things, and especially the next one as we do that. Well, it's not working out, so we can go ahead and sketch it ourselves. Really, we can put this on a coordinate plane. Let's just do that. So here's our coordinate plane. And we can start thinking through this. We're setting up an integral, so we want to integrate. And if we take a look at just one rectangular strip, I'm just going to put a line here to show one rectangular strip. We can think through this. We know it's our weight density, which was 4,000. Times the depth. Well, same idea here. To find the depth or how deep this strip is, the whole thing is 5 meters deep, and we want to subtract the y value that we're on. And then we want to find the area. Well, the area is length times our width. Well, our width is going to be dy again, but our length actually changes. It's not a rectangle. This changes. So what we need to do here is we need to find this x value. Well, this x value is going to change. So we have to find, in this case, the equation of a line. So over on the side here, we need to find the equation of this line, y equals mx plus b. So the slope of this line, well, we know this is 8 long and this is 10. So we can find our slope because it's going up 6. So our rise is 6 and our run is 2. So our slope is 6 over 2. And we know a point that it goes through, this point right here. This is the point 8, 0. So x is 8 when y is 0. That can help us find b. So this is 3 times 8 is 24. Subtract 24 from both sides and we get b is negative 24. So we know y equals, our slope is 6 over 2, which is 3, x minus 24. Now we're actually more concerned with the length of this, so the x value, so we need to solve for x. So we can add 24 to both sides, equals 3x, multiply by 1/3, and we get x is 1/3 y, and then 1/3 of 24 is 8. So there is the length of this little rectangle. So 1/3 y plus 8. And then again, our width of this rectangle is dy. And then we need to put our values in here for our integral. Well, we want to integrate, this is in terms of y, from 0 up to 5. So 0 to 5. And that's all it asked for. It asked for express the total force on the end of the tank as a definite integral. If we wanted to integrate this, we could multiply out, but there it is, the definite integral we would use. Last example here, this is another one, a cylindrical tank, 20 meters long, whose radius, don't really want this here yet, is 4 meters as shown, is half filled with oil, whose weight density is 3,000 newtons per cubic meter. Set up an integral whose evaluation will yield the total force exerted by the oil on one end of the tank. So here we have a cylindrical tank, and we need to set this up on a graph. Now, since it's a circle, our base is a circle here, the easiest way to graph a circle, or actually the easiest way to come up with the equation for the circle, is if that circle is centered on the origin. And so that's how we're going to draw our circle on the graph. We're going to go ahead and center at the origin. There's a few other things on here. We should know our equations of circles, so it's centered at the origin, so it's just x squared plus y squared equals the radius squared. We're told here that the radius was 4. Well, how are we going to set up this integral? Let's just start with our weight density. In this case is 3,000. The depth. Now this is different. Before, on our other two, our graph was set up in the first quadrant, and we could do 5 minus y in those cases. But this time we're below the x-axis, and so our depth here, like if we were picking here, let's say this was a 3. Actually, it would be negative 3 on our graph. This is a negative 3. So how deep is that? Well, that's 3 meters deep. So we don't want negative 3 meters deep. We want 3. So our depth here is just negative y. And thinking here, we could put negative 3 in there. So negative 3, our depth would be 3. So that's our depth times the area. So our area is length times width. So we're going to have that dy again. So we have this change in y, which we know is a dy. But we want to find this width. Well, that's an x value again. It's our x. Actually, it's two x's. So let's write that. It's going to be 2x dy. Well, we can't integrate this in terms of y with an x in here, so we need to solve our equation here for x. And so we could subtract y squared from both sides. We get 16 minus y squared, taking the square root, and we'll just do the positive part. We get the square root of 16 minus y squared. So we have a couple other things to do here. So we have 3,000. Let's actually write that as negative 3,000y right now. Now we could actually do 6,000, but 2x. So we just found that x is equal to the square root of 16 minus y squared. And our width is dy. And what are our values that go here on our integral? Well, we are integrating from our lowest point here, which is, since the radius was 4, that's going to be negative 4, all the way up to 0. So from negative 4 to 0. And that's the integral we want. We could put the negative 6,000 out here. Sorry about that, didn't do that very well. Negative 4 to 0, and then we have y times the square root of 16 minus y squared dy. So there is the integral that we could evaluate. It doesn't ask us to. We should know how to do that with not too much difficulty by now. Just so you know, we chose our circle to be centered at 0. We could, if we wanted to, have the base or the bottom of the circle here at 0. And this is going to be a little bit in the way. Well, not too bad. So we could have used a different circle and come up with a different integral, but usually for a circle centered at the origin is going to be easiest. Notice, just real quick, again, the length of this did not matter.